Welcome to Digital Training Hub. It is a great pleasure to welcome you to this session on digital evolution in computing, a journey that has transformed how we live, work, and connect. Today, we stand at the crossroads of unprecedented technological advancements, where computing continues to push the boundaries of possibility. From the early days of mainframe computers to the era of artificial intelligence, cloud computing, and quantum computing, digital evolution has redefined industries, enhanced efficiencies, and created limitless opportunities. The power of computing is no longer confined to research labs. It is embedded in our daily lives, influencing education, healthcare, finance, and governance. As we navigate this digital era, we must embrace innovation, adaptability, and security. With advancements in big data, cybersecurity, automation, and artificial intelligence, the role of computing is more critical than ever. It is up to us, professionals, educators, and innovators, to harness this power responsibly and drive sustainable digital transformation. Let us use this platform to exchange ideas, explore new possibilities, and shape the future of computing together. Welcome, and I look forward to an insightful and inspiring discussion. Thank you. Mechanical calculators. A glimpse into early computing before the rise of modern digital computers. Mechanical calculators played a crucial role in performing arithmetic operations efficiently. These devices, developed between the 17th and 20th centuries, were the foundation of automated computing and paved the way for modern-day electronic calculators and computers. Early computing devices like the abacus and slide rule paved the way for mechanical calculators such as Pascal's Pascaline and Leibniz's stepped reckoner. These early tools automated basic arithmetic calculations, laying the groundwork for the digital revolution. Mechanical calculators. 1. Early mechanical calculators. Pascaline, 1642, invented by Blaise Pascal. It was one of the earliest mechanical adding machines designed to assist with tax calculations. Leibniz's stepped reckoner, 1673, created by Gottfried Wilhelm Leibniz. This improved Pascal's design by enabling multiplication and division. 2. 19th century advancements. Charles Babbage's difference engine, 1822. Although never fully completed, this was a mechanical device designed to compute polynomial functions. Arithmometer, 1820s to 1850s, developed by Thomas de Colmar. It was the first commercially successful mechanical calculator. 3. 20th century mechanical calculators. Comptometer, 1887, a key-driven adding machine used extensively in business. Curta calculator, 1940s, a compact, portable mechanical calculator popular before the rise of electronic calculators. Mechanical cash registers and accounting machines, widely used in banking and business operations. 4. The decline of mechanical calculators. With the advent of electronic calculators in the 1960s and 1970s, mechanical calculators became obsolete. Companies like Casio, Hewlett-Packard, and Texas Instruments revolutionized computing with faster, more efficient digital alternatives. 5. Legacy of mechanical calculators. Mechanical calculators laid the groundwork for modern computing, automation, and data processing. Their principles influenced the design of early computers, leading to the digital revolution we experience today. Vacuum tubes. The building blocks of early computing. The emergence of vacuum tubes in the mid-20th century marked a significant leap forward in computing technology. These glass-encased electronic components functioned as amplifiers and switches, enabling the manipulation of electrical signals in early computers. Despite their size and propensity for overheating, vacuum tubes formed the basis of the first generation of electronic computers, such as the ENIAC, electronic numerical integrator and computer. The utilization of vacuum tubes in computing systems represented a paradigm shift, allowing for faster and more reliable electronic computation than previously thought possible. Vacuum tubes. The building blocks of early computing. 1. What are vacuum tubes? Vacuum tubes are electronic devices that control the flow of electric current in a vacuum-sealed glass or metal tube. They were widely used in early computers, radios, and televisions before the invention of transistors. 2. Role of vacuum tubes in computing. Used as switches and amplifiers in early computers. Allowed the first-generation computers, 1940s to 1950s, to perform calculations and process data. Replaced mechanical relays, making computers faster and more reliable. 3. Key computers using vacuum tubes. ENIAC, 1946. The first general-purpose electronic computer, using 17,468 vacuum tubes. UNIVAC I, 1951. The first commercially available computer, using vacuum tube technology. IBM 701, 1952. IBM's first large-scale electronic computer. 4. Limitations of vacuum tubes. Large size, computers filled entire rooms. High power consumption, generated a lot of heat, requiring cooling systems. Frequent failures, tubes burned out often, causing downtime. 5. The transition to transistors. By the late 1950s, vacuum tubes were replaced by transistors, which were smaller, faster, more energy efficient, more reliable. This transition marked the beginning of second-generation computers and set the stage for modern digital computing. The transistor revolution. The birth of modern computing. The invention of transistors in 1947 sparked a revolution in electronics, replacing bulky vacuum tubes with compact, reliable semiconductor devices. Transistors paved the way for smaller, faster, and more efficient computers. 1. What is a transistor? A transistor is a semiconductor device used to amplify or switch electronic signals and electrical power. Invented in 1947 by John Bardeen, Walter Brattain, and William Shockley at Bell Labs, transistors revolutionized electronics and computing. 2. How transistors transformed computing. Before transistors, computers relied on bulky, heat-generating vacuum tubes. The transistor revolution led to smaller computers, reduced size significantly compared to vacuum tube-based computers. Lower power consumption, less heat, making systems more efficient. Greater reliability, fewer failures and longer operational life. Increased speed, faster signal processing, leading to better performance. 3. The rise of second-generation computers, 1950s to 1960s. Transistors replaced vacuum tubes, leading to faster and more efficient computers. IBM 1401, 1959, one of the first successful transistorized computers. Paved the way for integrated circuits, ICs, in the 1960s. 4. The impact beyond computing. The transistor revolution influenced multiple industries. Small diamond telecommunications led to compact radios, telephones, and satellite communications. Small diamond consumer electronics enabled the development of televisions, hearing aids, and portable devices. Small diamond space exploration. NASA relied on transistor-based computers for early space missions. 5. The path to microprocessors. The miniaturization of transistors led to the invention of integrated circuits, ICs, and later, microprocessors in the 1970s, ushering in the era of personal computers and modern digital technology. Conclusion. The transistor revolution transformed the world, making computers faster, smaller, and more affordable, setting the foundation for today's advanced computing and AI-driven systems. Integrated circuits, ICs, the foundation of modern electronics. Integrated circuits emerged in the late 1950s, integrating multiple transistors onto a single chip. These circuits dramatically reduced the size and cost of computers while increasing their processing power, ushering in the semiconductor era. 1. What is an integrated circuit? An integrated circuit, IC, is a miniaturized electronic circuit consisting of multiple transistors, resistors, capacitors, and diodes embedded onto a small semiconductor chip, usually made of silicon. ICs revolutionized electronics by enabling complex functionalities within a compact design. 2. The birth of integrated circuits. Invented in 1958-1959 by Jack Kilby, Texas Instruments, and Robert Noyce, Fairchild Semiconductor. Moved away from bulky discrete components by integrating multiple functions onto a single chip. 3. Advantages of ICs over previous technologies. Smaller size enabled miniaturization of electronic devices. Lower power consumption, reduced heat and energy use. Increased reliability, fewer failures compared to transistors and vacuum tubes. Mass production made electronic devices cheaper and more accessible. 4. The rise of third-generation computers, 1960s to 1970s. Computers became faster, smaller, and more powerful. The IBM system, 360, 1964, was one of the first commercial computers to use ICs. Laid the foundation for the development of microprocessors in the 1970s. 5. Impact on technology. ICs played a key role in advancing. Small diamond computers enabled personal computers, laptops, and servers. Small diamond telecommunications powered mobile phones, internet routers, and fiber optics. Small diamond consumer electronics led to digital cameras, smart TVs, and gaming consoles. Small diamond medical devices improved MRI scanners, pacemakers, and hearing aids. Small diamond space exploration used in satellites, spacecraft, and planetary rovers. 6. Evolution to microprocessors and beyond. The advancement of IC technology led to microprocessors, 1970s. The entire CPU on a single chip, e.g., Intel 4004. Very large-scale integration, VLSI, 1980s to 1990s, millions of transistors per chip. Modern processors, 2000s present, billions of transistors enabling AI, IoT, and quantum computing. Conclusion: integrated circuits transformed the world, making modern computing, communications, and automation possible. From smartphones to supercomputers, ICs remain at the heart of technological evolution. Personal computers, PCs, revolutionizing everyday computing. The 1970s saw the rise of personal computers, bringing computing power to individuals. PCs from companies like Apple and IBM democratized technology, transforming how people work, communicate, and access information. 1. What is a personal computer? A personal computer, PC, is a small, affordable, and user-friendly computing device designed for individual use. Unlike earlier mainframe and mini-computers, which were large and expensive, PCs brought computing power to homes, offices, and schools. 2. The birth of personal computers. 1971. The microprocessor, the invention of the Intel 4004, allowed the entire CPU to fit on a single chip, making PCs possible. 1975. The Altair 8800, one of the first commercial PCs, based on the Intel 8080 microprocessor. 1977. The Trinity of early PCs. The Apple II, Commodore PET, and Tandy TRS-80 set the foundation for the PC industry. 1981. IBM PC. IBM introduced its IBM 5150 PC, running Microsoft's MS-DOS, setting the standard for modern personal computers. 3. Evolution of personal computers. 1980s. The rise of graphical user interfaces, GUI. Apple introduced the Macintosh, 1984, with a mouse-driven GUI. Microsoft released Windows 1.0, 1985, making PCs more user-friendly. 1990s. The Internet boom and multimedia revolution. Faster Pentium processors enabled gaming, graphics, and Internet browsing. The World Wide Web, WWW, became accessible, changing communication and business. 2000s present. Mobility, cloud computing, and AI. Laptops, tablets, and smartphones became popular. Cloud computing allowed online storage and remote access. AI and smart assistants, e.g., Siri, Cortana, Google Assistant, enhanced user experience. 4. Impact of personal computers. Education and research, online learning, simulations, and digital libraries. Business and productivity, word processing, spreadsheets, and automation. Entertainment, gaming, streaming, and social media. Communication, email, video calls, and collaboration tools. Conclusion: personal computers transformed society, making computing accessible, powerful, and essential for work, education, and entertainment. Today, innovations like AI, cloud computing, and quantum computing continue to shape the future of PCs. Graphical User Interface, GUI, making computers user-friendly. 1. What is a graphical user interface, GUI? A graphical user interface, GUI, is a visual way of interacting with a computer using graphical elements like windows, icons, buttons, and menus instead of text-based commands. GUIs make computers easier to use by allowing users to interact through point-and-click actions, typically with a mouse, touchscreen, or stylus. 2. The evolution of GUI. 1963. Sketchpad, the first graphical computer interface, developed by Ivan Sutherland at MIT. 1973. Xerox Alto, the first modern GUI computer, featuring windows, icons, and a mouse. 1984. Apple Macintosh, the first commercially successful GUI-based PC, making computing accessible to the public. 1985. Microsoft Windows 1.0 introduced GUI elements to IBM-compatible PCs, evolving into the dominant operating system. 1990s to 2000s. Modern GUI systems, Apple's macOS, Microsoft Windows, and Linux desktop environments refined GUI design. 2010s present. Touchscreen GUIs, smartphones, tablets, and hybrid PCs adopted touch-based interfaces. 3. Key features of a GUI. Windows organizes different tasks into separate sections. Icons, small images representing applications, files, or functions. Menus, drop-down or pop-up lists for selecting commands. Buttons, clickable elements for performing actions. Scroll bars and sliders, allows users to navigate content easily. Drag and drop, move files and objects intuitively. 4. Advantages of GUI over text-based interfaces. Easier to learn, no need to memorize complex text commands. More efficient, faster navigation and multitasking. Visually appealing, intuitive designs and customizable themes. Better accessibility, supports touch, voice, and assistive technologies. 5. Impact of GUI on modern computing. Personal computers, Microsoft Windows, macOS, and Linux GUIs dominate the market. Mobile devices, iOS and Android use touch-based GUIs. Web applications, websites and apps rely on graphical interfaces for user engagement. Gaming and virtual reality 3D interfaces create immersive experiences. Smart home and IoT, smart TVs, watches, and appliances use intuitive GUIs. Conclusion: graphical user interfaces revolutionized computing, making it accessible to non-technical users. As technology advances, AI-powered GUIs, AR, VR interfaces, and voice-based systems are shaping the future of user interactions. The Internet Age. A connected e-internet connected billions of devices and users worldwide, transcending geographical boundaries and enabling seamless communication and collaboration. 2. The evolution of the Internet. 1960s. The birth of networking. The ARPANET, 1969, was developed by the U.S. Department of Defense, laying the groundwork for the modern Internet. 1980s. Internet Protocols and Expansion. TCP, IP, 1983, became the standard protocol for data exchange. Domain Name System, DNS, 1984, simplified website addresses. 1990s. The World Wide Web, WWW, Revolution. 1991. Tim Berners-Lee introduced the World Wide Web, WWW, allowing websites to be accessed via browsers. 1993. The first web browser, Mosaic, made Internet navigation user-friendly. 1995. Companies like Amazon, eBay, and Yahoo started online businesses. 2000s. Broadband, social media, and e-commerce. High-speed broadband internet replaced slow dial-up connections. Google, Facebook, YouTube, and Twitter transformed how people interacted. Online banking and e-commerce became mainstream. 2010s present. Mobile, cloud, and AI-driven internet. Smartphones and 4G, 5G networks enabled internet access anywhere. Cloud computing, e.g., Google Drive, Oz, stored data online. AI and IoT-powered smart assistants, Siri, Alexa, and automated services. 3. Impact of the Internet Age. Instant communication, email, video calls, and social media connect people globally. E-commerce and digital payments, Amazon, PayPal, and mobile banking revolutionized trade. Education and e-learning, online courses, virtual classrooms, and research databases. Work and collaboration, remote work, cloud-based tools, Google Workspace, Microsoft Teams. Entertainment and streaming, Netflix, YouTube, and gaming platforms changed media consumption. 4. The future of the Internet: 6G and faster connectivity, ultra-fast internet speeds for seamless interaction. AI and personalized web experiences, smarter search engines, virtual assistants. Decentralization and Web3 blockchain-based applications, secure online transactions. Metaverse and virtual reality 3D immersive digital experiences. Conclusion: the Internet age has transformed every aspect of life, making the world more connected, digital, and efficient. As AI, 5G, and Web3 evolve, the Internet will continue to shape the future in unimaginable ways. Mobile computing. Revolutionizing connectivity 1. What is mobile computing? Mobile computing refers to the ability to access, process, and transmit data wirelessly using portable devices like smartphones, tablets, laptops, and wearables. It enables users to stay connected anytime, anywhere, making it a cornerstone of the digital age. 2. Evolution of mobile computing. 1G, 1980s, early mobile communication, basic voice calls using analog cellular networks. 2G, 1990s, SMS and digital networks, introduction of text messaging and improved call quality. 3G, 2000s, mobile internet, faster data speeds enabled web browsing and multimedia. 4G LTE, 2010s, high-speed connectivity, streaming, video calls, and cloud computing became seamless. 5G, 2020s, ultra-fast and low latency, AI, IoT, and real-time applications revolutionized industries. 6G and beyond, future, AI-driven smart networks, holographic communication, and ultra-fast data speeds. 3. Key components of mobile computing: small diamond wireless networks, Wi-Fi, 4G, 5G, and satellite networks enable seamless connectivity. Small diamond cloud computing, access to applications and data storage from remote servers. Small diamond mobile hardware, smartphones, tablets, laptops, and wearable devices. Small diamond software and apps, operating systems, Android, iOS, and mobile applications. Small diamond Internet of Things, IoT, smart devices communicate wirelessly in real time. 4. Applications of mobile computing: healthcare, telemedicine, remote patient monitoring, and AI-driven diagnostics. Education, e-learning platforms, digital classrooms, and interactive content. Finance and banking, mobile payments, digital wallets, and online transactions. Transportation, ride-hailing apps, Uber, Bolt, GPS navigation, and fleet management. E-commerce, mobile shopping, AI-driven recommendations, and instant deliveries. Business and productivity, remote work, cloud collaboration, and mobile CRM systems. Entertainment, streaming services, gaming, and social media engagement. 5. Future of mobile computing: 5G and 6G networks, faster, more reliable connectivity with ultra-low latency. AI and machine learning, smarter assistants, predictive analytics, and automation. Augmented and virtual reality, AR, VR, enhanced mobile experiences in gaming, education, and work. Edge computing, faster processing closer to users, reducing data transmission delays. Wearable technology, smartwatches, AR glasses, and health monitoring devices. Enhanced security measures, AI-driven cybersecurity, biometrics, and encryption. 6. Challenges and considerations: security risks, cyberattacks, data breaches, and phishing scams. Battery life and energy efficiency, need for longer battery life and sustainable solutions. Connectivity limitations, internet access gaps in remote and rural areas. Privacy concerns, ethical handling of user data and surveillance issues. Conclusion: mobile computing has transformed global communication, business, and daily life. With advancements in AI, 5G, IoT, and cloud computing, the future holds exciting possibilities. However, security, privacy, and infrastructure development must evolve alongside technology. Artificial intelligence, AI, transforming the future. 1. What is artificial intelligence, AI? Artificial intelligence, AI, is the simulation of human intelligence in machines, enabling them to learn, reason, and make decisions. AI-powered systems analyze vast amounts of data to identify patterns, automate tasks, and solve complex problems faster than humans. 2. Evolution of AI 1950s to 1970s. Early AI research. Alan Turing proposed the Turing test to assess machine intelligence. 1980s to 2000s. AI growth in machine learning, neural networks and algorithms improved decision-making. 2010s present. AI boom, deep learning, big data, and AI-driven automation revolutionized industries. 3. Key AI technologies and concepts. Small diamond machine learning, ML. AI learns from data and improves over time. Example. Netflix recommendations. Small diamond deep learning uses neural networks for advanced decision-making. Example. Self-driving cars. Small diamond natural language processing, NLP. AI understands and generates human language. Example. ChatGPT, Siri. Small diamond computer vision. AI interprets images and videos. Example. Facial recognition, medical imaging. Small diamond robotics and automation. AI-powered robots perform complex tasks. Example. Factory automation, drones. Small diamond generative AI. AI creates content, from images to text and videos. Example. ChatGPT, DALL-E. 4. AI applications in different industries. Healthcare. AI diagnoses diseases, assists in robotic surgeries, and enables personalized treatments. Transportation. Self-driving cars, traffic management, and route optimization. Business and finance, fraud detection, AI-powered chatbots, and financial forecasting. Education. AI tutors, adaptive learning, and automated grading. Climate and sustainability. AI-driven weather predictions and energy optimization. Entertainment. AI-generated content, deepfake technology, and personalized recommendations. 5. Future prospects of AI. Augmented workplaces. AI will enhance productivity, automate repetitive tasks, and assist professionals. Explainable AI, XAI. Ensuring transparency in AI decision-making to build trust. Human-AI collaboration. AI as an assistant rather than a replacement for human workers. Ethical AI and regulations, preventing bias, ensuring security, and setting global AI governance standards. 6. Challenges and ethical considerations. Bias and fairness. AI models must be trained on diverse datasets to prevent discrimination. Privacy and data security, protecting user data from misuse and cyber threats. Job displacement. AI automation could replace certain jobs, requiring workforce reskilling. Misinformation and deepfakes. AI-generated fake content poses risks in media and politics. Conclusion. AI is transforming industries and daily life, with innovations in healthcare, finance, education, and more. However, ethical considerations and regulations must guide AI development to ensure a fair, secure, and human-centric future. Quantum computing. The future of supercomputing. 1. What is quantum computing? Quantum computing is a cutting-edge technology that leverages the principles of quantum mechanics to process information at unprecedented speeds. Unlike classical computers that use bits, zeros and ones, quantum computers use qubits, which can exist in multiple states simultaneously due to superposition and entanglement. 2. Key concepts in quantum computing. Small diamond qubits, quantum bits. Unlike classical bits, qubits can be 0, 1, or both at the same time, superposition. Small diamond superposition. A qubit can exist in multiple states simultaneously, increasing processing power. Small diamond entanglement. Qubits can be interconnected, meaning a change in one affects the other instantly. Small diamond quantum tunneling. Qubits can bypass barriers in calculations, solving complex problems faster. 3. How quantum computers differ from classical computers. 4. Applications of quantum computing. Healthcare and drug discovery, simulating molecular structures for new medicine development. Finance and cryptography, cracking and enhancing encryption for cybersecurity. Artificial intelligence, AI, and machine learning, faster and more efficient data analysis. Climate and weather forecasting, high-accuracy climate modeling and disaster prediction. Supply chain and logistics, optimizing complex logistical networks. Scientific research, solving physics, chemistry, and biological mysteries. 5. Challenges in quantum computing. Hardware limitations. Building stable quantum processors is extremely complex. Error rates and stability. Qubits are highly sensitive and require error correction mechanisms. High costs. Quantum computing technology is expensive and requires specialized infrastructure. Data security concerns. Quantum computers could break traditional encryption methods, leading to cybersecurity risks. 6. Future of quantum computing. Quantum supremacy, achieving calculations that classical computers cannot solve. Integration with AI and big data, enhancing AI algorithms and data analytics. Quantum cloud computing. Companies like IBM, Google, and Microsoft are developing cloud-accessible quantum systems. Breakthrough in cryptography. Development of quantum-resistant encryption for cybersecurity. Conclusion. Quantum computing is poised to revolutionize industries by solving problems that are impossible for classical computers. However, challenges like hardware limitations, stability, and security risks must be addressed before widespread adoption. Cybersecurity challenges in the digital age. Lock PC. As technology advances, so do the cybersecurity threats that organizations and individuals face. Cybercriminals are continuously developing new attack methods, making cybersecurity a critical concern for businesses, governments, and individuals. 1. Top cybersecurity challenges. Microbe 1. Malware and ransomware attacks. Malicious software, malware, such as viruses, trojans, and ransomware can steal data, damage systems, or hold data hostage until a ransom is paid. Example: WannaCry ransomware attack, 2017, affected over 200,000 computers worldwide. Lock 2. Phishing and social engineering. Cybercriminals use deceptive emails, fake websites, and phone calls to trick users into revealing passwords, credit card numbers, or personal data. Example: business email compromise, BEC. Scams cost companies billions annually. Globe 3. Cloud security risks. As businesses move to cloud-based services, they face data breaches, misconfigurations, and unauthorized access. Weak encryption and poor access controls can expose sensitive data. Bank 4. Identity theft and credential attacks. Hackers steal passwords and personal information through data breaches or brute force attacks. Stolen credentials are often sold on the dark web and used for fraud. Door 5. Insider threats. Employees or contractors with access to systems may intentionally or accidentally cause security breaches. Human error remains a major cybersecurity vulnerability. Globe 6. Internet of Things, IoT, vulnerabilities. Millions of connected IoT devices, smart home devices, wearables, and industrial sensors are often insecure and easily hacked. Example: infected IoT devices were used to launch the Mirai botnet DDoS attack in 2016. Shield 7. Lack of cybersecurity awareness. Many organizations suffer cyber attacks due to poor training, weak passwords, and lack of awareness. Employees must be educated on safe online practices to prevent attacks. Key 8. Weak or outdated security systems. Organizations using outdated software, unpatched systems, and weak encryption are at high risk. Zero-day vulnerabilities allow hackers to exploit flaws before companies patch them. Globe 9. Nation-state cyber threats and cyber warfare. Governments and state-sponsored hackers engage in espionage, cyber attacks on infrastructure, and election interference. Example: Stuxnet, 2010. A cyber weapon that targeted Iran's nuclear program. Brain 10. AI-powered cyber threats. Hackers now use AI and machine learning to launch sophisticated attacks like deepfake scams, automated phishing, and AI-powered malware. Defensive AI is needed to counter these threats. 2. Strategies to combat cybersecurity challenges. Checkmark. Implement strong authentication. Use multi-factor authentication, MFA, and strong passwords. Checkmark regular security updates and patching, keep software and systems updated to fix vulnerabilities. Checkmark cybersecurity awareness training, educate employees and users on phishing, social engineering, and safe online behavior. Checkmark advanced threat detection and response, use AI-driven cybersecurity solutions to detect threats in real time. Checkmark secure IoT devices, use strong encryption, firmware updates, and network segmentation for IoT security. Checkmark zero trust security model, assume no device or user is automatically trusted, verify access constantly. Checkmark cloud security best practices, encrypt data, use access controls, and monitor cloud activity. Checkmark data backups and disaster recovery plans, regularly backup data and have incident response plans in place. Conclusion: cybersecurity challenges are evolving as hackers adopt more sophisticated tactics. Businesses, governments, and individuals must take a proactive approach to cybersecurity by implementing strong security measures, continuous monitoring, and cybersecurity awareness training. Ethical considerations in the digital age. The widespread adoption of computers raises important ethical considerations, such as data privacy, algorithmic bias, and the impact of automation on jobs. Balancing technological advancement with ethical principles is essential for creating a more equitable and inclusive society. 1. Key ethical considerations in the digital age. 1. Privacy and data protection. Personal data is constantly collected by social media, websites, and smart devices. Ethical question: how should companies balance user convenience and data privacy? Best practice: follow data protection laws, GDPR, Data Protection Act, obtain user consent, and implement strong encryption. 2. Digital surveillance and government control. Governments monitor digital activities for national security, but this can infringe on personal freedom. Ethical question: to what extent should governments have access to private digital information? Best practice: ensure transparent and justified surveillance policies with public accountability. 3. Artificial intelligence, AI, ethics. AI is used for hiring, policing, healthcare, and decision-making, but it can be biased or lack transparency. Ethical question: how do we ensure AI systems are fair and unbiased? Best practice: implement ethical AI guidelines, use diverse datasets, and ensure human oversight in AI decisions. 4. Digital divide and access to technology. Not everyone has equal access to technology and the internet, leading to educational and economic inequalities. Ethical question: how do we ensure equal access to digital resources for all? Best practice: governments and organizations should promote digital inclusion by expanding internet access and digital literacy programs. 5. Misinformation and fake news. False information spreads quickly online, influencing elections, public health, and social beliefs. Ethical question: should governments regulate online content, or does this violate free speech? Best practice: encourage fact-checking, digital literacy, and responsible social media policies. 6. Cybersecurity and ethical hacking. Ethical hackers test security systems, but where is the line between ethical and unethical hacking? Ethical question: is hacking justified if it prevents greater harm? Best practice: ethical hacking should be conducted legally, with consent, and for the benefit of security improvements. 7. Social media ethics. Platforms use algorithms to influence user behavior, sometimes promoting addiction, hate speech, or divisive content. Ethical question: are social media companies responsible for user behavior and mental health issues? Best practice: implement ethical content moderation, transparent algorithms, and user protection policies. 8. Digital workplace ethics. Employers use tracking tools to monitor employee productivity and emails. Ethical question: how much digital surveillance in the workplace is acceptable? Best practice: employers should clearly disclose monitoring policies and respect employee privacy. 9. Cryptocurrency and ethical finance. Digital currencies like Bitcoin enable financial freedom, but also fraud, money laundering, and scams. Ethical question: how do we regulate digital currencies without stifling innovation? Best practice: governments should introduce clear cryptocurrency regulations to prevent abuse while allowing innovation. 10. Ethical AI in hiring and decision-making. AI is used to screen job applicants, approve loans, and analyze employee performance, but it may be biased. Ethical question. Should AI make life-changing decisions without human intervention? Best practice. AI-based decisions should be transparent, fair, and always reviewed by humans. 2. Best practices for ethical digital development. Transparency, fairness, privacy protection, cybersecurity measures, public awareness and digital literacy. Future prospects of the digital age. The future of digital evolution is shaped by rapid advancements in artificial intelligence, AI, the Internet of Things, IoT, quantum computing, and Web3 technologies. As digital transformation accelerates, industries, businesses, and daily life will experience revolutionary changes. 1. Key technologies shaping the future. Small diamond. Artificial intelligence, AI, and machine learning. AI-powered automation will optimize industries like healthcare, finance, and manufacturing. Chatbots, virtual assistants, and autonomous systems will enhance efficiency. Small diamond. 5G and beyond, 6G, satellite internet, faster, more reliable internet will power smart cities, remote work, and IoT devices. Starlink and other satellite networks will bring connectivity to rural areas. Small diamond. Quantum computing. Ultra-powerful computers will revolutionize encryption, simulations, and problem-solving. Industries like pharmaceuticals and finance will benefit from advanced computations. Small diamond. Web3 and blockchain technology. Decentralized applications, DApps, will redefine finance, governance, and digital ownership. Cryptocurrencies, NFTs, and smart contracts will shape the digital economy. Small diamond. Metaverse and extended reality, XR, AR, VR, Mr. Virtual and augmented reality, VR, AR, will transform gaming, education, and remote collaboration. The metaverse will create immersive digital spaces for work and social interaction. Small diamond. Cybersecurity and data privacy. AI-driven threat detection will combat sophisticated cyber attacks. Privacy-enhancing technologies, PETs, will ensure safer digital transactions. Small diamond. Autonomous vehicles and smart infrastructure. Self-driving cars, drones, and smart traffic systems will enhance transportation. AI-driven urban planning will create sustainable, tech-enabled cities. 2. Future impact on industries. Healthcare. AI-driven diagnostics, robotic surgeries, and telemedicine will enhance medical care. Education, virtual learning, AI tutors, and adaptive learning platforms will revolutionize education. Workforce and remote collaboration, hybrid work environments, AI-powered productivity tools, and virtual offices. E-commerce and digital payments, personalized shopping experiences with AI-driven recommendations. Climate and sustainability, green technologies, AI-driven climate models, and renewable energy solutions. 3. Challenges and ethical considerations. Data privacy and security risks, ensuring safe AI and blockchain usage. Digital divide, bridging the gap between tech-advanced and underdeveloped regions. Ethical AI use, preventing bias, misinformation, and job displacement. Conclusion. The future of digital evolution is limitless, with groundbreaking technologies shaping a smarter, more interconnected world. As we embrace AI, Web3, the metaverse, and quantum computing, we must also address cybersecurity, ethics, and inclusivity to ensure a balanced digital future. Would you like a deep dive into a specific emerging technology or its impact? As we reflect on the journey of digital evolution, it is evident that technology has transformed every aspect of our lives, from the early days of mechanical calculators to the rise of AI, quantum computing, and the Internet of Things, IoT. Each phase of digital evolution has not only enhanced efficiency and connectivity but has also introduced new challenges, including cybersecurity risks, ethical dilemmas, and the digital divide. Moving forward, we must embrace innovation responsibly, ensuring that digital advancements serve humanity equitably and ethically. Governments, businesses, and individuals must work together to create a secure, inclusive, and sustainable digital future. As we step into the next era of AI, automation, and digital intelligence, let us remain vigilant, adaptive, and ethical, making sure that technology remains a force for good. The digital revolution is far from over. The future is in our hands. Rocket, let's continue shaping a smarter, safer, and more connected world. Thank you for joining us on this journey through the evolution of computers. For further inquiries or collaborations, please feel free to contact us.